Welcome to Nature in Code. This video marks the beginning of Chapter 7, Epidemics, the Spread of Infectious Diseases. Infectious diseases are diseases like the cold, flu, HIV/AIDS, SARS, measles, Ebola, polio, whooping cough, you name it, the list is almost endless. These are diseases that are caused by an infectious agent, typically a microorganism such as a virus, a bacteria, or a fungus. And when these microorganisms enter our body, they can cause an infection and they can make us sick, and then we call them pathogens. Now, it's bad enough that these pathogens can make us sick. The real problem is that once they enter our bodies, not only may we get sick, but we may actually pass the pathogens on, pass the microorganisms on to other individuals, and then in turn make them sick. Now, not all microorganisms have the same effect, and sometimes even microorganisms that are known to be pathogenic in humans don't cause disease in all humans. In a previous video, we have already seen this process of hosts and parasites infecting hosts trying to avoid infection, and we've looked at this process in the context of coevolutionary dynamics. Now, in this chapter, we're not interested in that anymore. We're not interested whether a host gets sick or not. Just as long as a host passes on the infection, we are interested how, beginning from a single individual who introduces a disease, an infectious disease in a population, this disease can then spread through the population and cause an epidemic. And epidemics are still major threats to public health worldwide. It's much better now than it used to be. A little more than a century ago, infectious diseases were the major killer absolutely everywhere in the world. Many children didn't make it past age 5. There were no vaccines, there were no antibiotics, but nowadays modern public health systems have helped us keep many of these killer diseases in check, but not everywhere, and there are constantly new diseases emerging. So we always have to be on the lookout, and a basic understanding of how these diseases spread in a population is very helpful. Now, we will build a virtual world in JavaScript where a single infectious individual starts infecting others and thereby starts an epidemic. And the model that we're going to use for this is again going to be an individual-based model. And it's a version of what we call the SIR model. And that stands for susceptible, infected, and recovered, or alternatively removed. Now, individuals are in one of those 3 states. So when they're susceptible and they're exposed to the disease, there's a chance that they become infected. Now, when they're infected, they're also infectious. So they can now infect other people, other susceptible individuals. After a while, we assume in our model that infected individuals recover. This is really the simplest model you can think of. In fact, there's a simpler model which is called SI. There's no recovered or removed state. Once you clear the infection, you simply go back to the susceptible state. However, in most human diseases, clearing an infection usually means building an immune response and an immune memory, and it means that you can't get infected anymore. So that's what recovered means. It means you're not infectious anymore, but you can also not be infected again. So since we build an individual-based model, we will model individuals as being in one of these 3 states, S, I, and R. And we have to think about 2 probabilities. The first probability is if you are indeed susceptible and you are now exposed to an infected individual, what is the probability per unit time, per time step, that you will become infected? This is not always guaranteed. There's a probability that this will happen. And we are going to call this infection probability per contact and unit time. We're going to call this beta. Okay, so I'm going to use the Greek letter beta here. Once you are infected, you will recover. So you will go from this now infected state to the recovered state. At each time step, this happens to you with a certain probability. So with a certain probability, and we call this probability gamma, you will recover. So you will transition from the infected state to the recovered state. As simple as that. Now, what we will do is we will implement this model in a grid, as we have done in Chapter 5. We could, of course, build a non-spatial model of this infectious disease process of an epidemic, but I think it's instructive to see what happens in a spatial model. It's also more fun to look at, I think. So let's go ahead and implement this in JavaScript. We'll start coding in the next video. See you there.